I would like to introduce Elena Dimitrova from Quality to tell you about their work.
Hi everyone. So in the spirit of improving dev life, I'm going to be talking about wiring upgradable contracts, or basically making the whole experience of writing code against this pattern more smooth for a developer. Basically putting the wiring to one side and just focusing on the work that you need to do. So first of all, I'm going to go through and present that pattern overall, because there's many different implementations of it. I want it to be clear what I'm talking about, and then just some dev tips around how you can automate particularly the wiring behind and the setup of it. So very widely speaking, there's two main schools of thought when it comes to contract upgradability. The first one is so-called eternal storage. As the name implies, that involves separating storage and data, separating the storage and the business logic, where the business logic owns and works with the data underneath. So essentially what you are upgrading is the business logic on top of the eternal storage, which is meant to stay immutable over time. So that's permanent on chain, and what you migrate is just the logic on top of it. This is the pattern that we used at Colony 2-3 years ago. I wrote a blog post back in 2016 outlining it, and it's still a very valid pattern that some people still use. However, a year ago, we found that our needs had grown, particularly in the amount of code that we have. If you've touched on the Colony network, it's pretty complex. And with the eternal storage pattern, there's a lot of reading and writing to storage, which when you have two separate contracts, adds up in cost, because the external, just looking up a value in an external contract is a touch more expensive than doing it internally. So all of that added up, and we need the cheap, more kind of scalable way to do that. Also, the Delegate proxy pattern that I'm going to cover today gives you something eternal storage doesn't, which is immutable addresses, meaning that you can still upgrade your code, but the address that people point to and work with is still the same. So diving into that a little bit more, I've just diagrammed a simple call chain using that pattern. I just want to highlight the three layers that we have, represented by three contracts. I'm going to go into a little bit more in code. So the first part is the ETH router, which, as the name suggests, routes calls from the user, and it's the first point of contact of either a user or contract, so something interacting with your system. So that's where the first all basic user calls land. The resolver is where things get looked up. It's basically the contract which pretty much only the router works with. It's a mapping of where essentially functions are implemented. So ETH router looks up the message signature, which is the byte for function signature of what the user has called. For example, if a user says, well, I want create colony to execute, that create colony is being looked up on the resolver, and the resolver says, well, that function is implemented in the colony contract, which is the implementation all the way at the back. So the implementation is pushed all the way away from the user, allowing them to work with a really simple, immutable contract, which is the ETH router that I'm going to show in a minute. So once that lookup has been done, ETH router does a delegate call onto the implementation that it now knows about, and optionally, if that function has a return parameter, it returns it back all the way to the user. So that's very simply the theory. I'll just go into the code of each one, and then I'll show you how it works in practice. ETH router, because it's the only mutable part of the pattern, it's used as the simplest possible contract that you can write, because it's deployed once and never changed. So I've abbreviated the fallback function, which is where all the magic happens. That's on the next slide, but pretty much that's the rest of it. There's only a single property, which is the resolver. The only thing it needs to know about is where to look up the function signatures, and a single function that sets the resolver, which is authorized. Like I said, the magic happens in the fallback function, which in Solidity gets executed if the call doesn't find a matching function in the contract. So a contract or a user calling ether with, let's say, create colony, ether doesn't have a function like that, so it just goes through here. So basically all the calls that the user executes are just like funneled through that fallback function. And the fallback function is generic enough to cater for everyone. So it, first of all, as we saw from the diagram, it does a lookup of the function signature in the resolver. And that destination address is implementation, let's say a colony address. Then it does the delegate call to that destination with the call data, and the parameter at the end is the return data size that we then copy from. So since the Byzantium hard fork, we now have these two very useful opcodes for that fallback function called return data copy and return data size that enable us to basically support any size or dynamic size return parameters. What I'm saying basically is with a single fallback function, you cater for every possible function execution in Solidity. So anything you channel through here will essentially execute in the context of the iterator and return back either a success, so the result of a delegate call in Solidity is either 1 or 0. 1 for success, where you return the data back to the user, and 0 for failure, where you revert. So that's really the iterator fallback where all the channeling through happens. Delegate calls, some of you may be familiar with if you work with libraries. So Solidity libraries work with delegate calls under the cover. So this is very similar, but it gives you a lot more control over the execution. Libraries are a bit more limited that way, but they're very useful with the iterator pattern. I've described that in that one call at the start. So the interesting thing about delegate call is that it allows you to execute code from the destination address in the context of the calling contract. So in that call that's executed there, things like this point to the iterator address. And more importantly, the storage references are all local. So whatever you're executing from that destination is literally pulled in the context of the iterator and executed and stored locally. So your contract implementation is just like a logical a definition of your functionality, but it holds no data. All the data is the iterator. That's really part of the magic, which also has some difficulties around that I'm going to highlight later. But it means that the only immutable part of your pattern is also the heavy, where the biggest amount of data is, well, the only place really where the data is stored. Also meaning that you don't need to migrate any of that when you do upgrades and migrations. So that's just a little bit around the delegate call. The resolver, which is the next part in that diagram, it's also a really simple but powerful contract. It acts as basically a mapping, a registrar of function signatures, which are the bytes for key in that mapping, to an implementation address. So, and it has the two functions at the top are reading and writing from that. It's as simple as that. The function at the bottom is simply like a help, a pure function that helps you get the function signature of a key. But what having a mapping here means is that at the iterator address you can have potentially an unlimited amount of code. It's superimposed in the fact that you have many different contracts in the background, but the limitations of how much code iterator can represent is potentially limitless. So at calling that was important, and part of our decision to go with this because our contracts were getting reasonably complex, reasonably heavy. We got very close to the block size limit on deploying a single contract, so we started to think of creative ways of expanding that. So this is very useful for very large code bases, or if you're getting near the block size limit. At the end, just showing how it wires up. This is using TruffleCon contract, just part of one of our tests. The example is wiring up a simple upgradable colony contract. So a contract that just has a single function of make tasks. So imagine let's do that in a pattern. So the first thing you do is you need to have an instance of each of the three layers from the first diagram I showed. A colony, a resolver, and e-router. E-router acts as our delegate proxy, so that's what I named it. Then you register that new function on the resolver, so e-router knows where to look stuff up. And then you set the resolver on the delegate proxy. So then you are in the whole chain kind of backwards, because things are dependent on each other. So e-router knows where the resolver is, the resolver knows where the implementation of make task is, and it all comes together at the bottom, which is, this is the weird part. So you're pointing a colony implementation at the delegate proxy address. So that delegate proxy is in fact an e-router. So what you're saying is, use that interface, but send all my calls to that really dumb contract with a single fallback function. Which is going to do all the magic, and none of that, all of that compiles and it's not going to fall apart, but it's a little bit weird having to do that. And then once you start calling that function on the colony, which is not a colony, it's actually a delegate proxy acting as a colony, then that make task will flow through the Callchain that we saw at the front. So it's going to go to e-router, that's not going to know where to send it, so looks it up in the resolver and so on and so on. And eventually, once that completes, that new task will end up in e-router storage, even though the mapping for tasks may be declared in the colony contract. Yeah, that's the thing in the end that we'll go into. So the two main, not problems, but developer kind of life got worse once we plugged it in. So the first thing we found was that we had to keep, updating the resolver mappings, because once you introduce a new function or add a new parameter to an existing function or add a new return value, that changed the whole function signature. So you have to re-register it in that middle tier in the resolver. And this is just, you don't need to see this, but you get the idea of how much code a single feature needed to change just for the plumbing of the resolver sitting in the middle. So that was difficult and very error prone, and you worked with byte-for signatures of functions, which wasn't easy as well. And then the second point, which you may have guessed, revolves around storage and how that works with superimposing storage onto e-router. So what we have to keep in mind is that every contract that e-router worked with and was wired to work with had to match the storage reference layout of the e-router. So if those two address fields in the implementation contract weren't there, what colony thinks is that in storage slot 0, it has variable x. So it has no concept of e-router storage layout. So if you have a function that sets variable x to 1, and that executes against e-router, it's going to store variable x or 1 into the owner field, which is stored slot 0. So we had to port the e-router, even though it was very simple, it still had two fields, an owner and a resolver. So all of our contracts really start with those two fields, because otherwise storage goes very, very wrong. And it continuously kind of came in the way of development as well, because you had to worry, well, how am I declaring, where am I declaring my storage variables? You know, you had to know about the tightly packing variables by the compiler. You have to know about how inheritance works. So inherited storage variables get inherited like falses first, and all of these things that you have to be aware of. So yeah, all of your contracts have to start with like that way. So colony knows that the first two slots actually, accounted for elsewhere and doesn't overwrite them. solve those two problems. We abstracted things, we broke down the problem and tried to solve it. So this is all concerning the implementation part, which sat at the far end of that diagram, which consisted originally of just a single calling contract. Because, well, one of the main problems was storage, as I said. So the first thing we did is take all storage variable declarations and just put them in one contract. We have one contract across all kind of logical sets of contracts that sits at the bottom that then everything inherits from. So calling storage is just purely used. It starts off with owner and resolver addresses declarations for each router, and then continues to provide all the storage variables that these other contracts need. So move all storage variables in one place. Second layer was to break down the actual business logic into separate logical pieces, because the resolver allowed us to do that. So the resolver, you can register any number of target contracts. Yes, you can have a function per contract, and that will still be fine. And those, as I said, inherited from calling storage, just so that have access into the storage variable declarations. And the other thing across the top is it's an interface, but it's not a Solidity interface, so don't understand it. So the contract starts with contract I-calling, not an interface I-calling. But it's actually the logical sense, an interface which constitutes of all the public and external functions of these three contracts. So anything your clients, whether it's a user or a contract, needs to interact with, it's in that interface contract. So it's all bundled together. That's where all about documentation is as well, so it's very nice to look at. And it provides a nice abstraction of, well, what do I need to register in my resolver? You know, it's not necessarily everything here, because like internal and private functions you don't need to register. And then, so now we've separated everything out and we've broken it down, divide and conquer. We scripted. So the registration changes. A script that does all of that at the background and is part of our Truffle migrations. So Truffle migration is very easy to kind of hook in external scripts into. Does, well, these four things. It takes that interface contract, which sits at the top of everything, and parses the JSON of it. So Truffle contract produces in the build folder by default these JSON definitions. Loop through the contracts that implement it and finds out where each function is actually done, and then does a register for each one of them. It does other things, like it doesn't allow you to register the same function signature twice. So you can do smart things in the script with it. And eventually, once it finishes, it just sets the resolver on each router, which is that wiring at the start that I showed. So now we have that script. You no longer, like, I didn't have to worry about any registrations of any function changes. I could just focus on functional implementation, and it all just worked. So it took a lot of load off us. Then going on to the second problem, which is more difficult to automate, the storage layout variables. The way we did that, so like I showed, we abstracted that into a single storage contract, which then we can simply parse and check that no state variables are declared anywhere else. So we have a white list of storage contracts, and that script is part of our continuous integration. And if it finds storage variables declared anywhere else in any other contract, it just blocks. So it becomes very easy once your storage variables are consolidated that way to actually analyze them and see if there's any potential storage clashes with upgrades specifically. We use the Solidity parser ANTLR for that, and filter out all state variables with the exception of constants, which actually don't occupy the storage slots. So constants in Solidity are synthetic sugar, basically. When the compiler compiles the contracts, when it finds a constant, it simply goes and replaces every occurrence of it with that constant value. So a constant never occupies a storage slot and you don't care about it. You can have as many of them as you want. So that's a script that does that. I'm gonna have the slides available, probably tweet about it so you guys have the link, but it's a Colony Network repo. And I've just put a link to where you can read about storage variables layout. I was thinking whether to do a demo of doing that in Remix and seeing if you can guys guess where, storage layouts, like where variables go in which storage slot. The long short of it is that so known variable sizes like uint256, an address, a boolean, all of them occupy a fixed amount of storage. Things like mappings, arrays, and structs have a pretty fancy way of determining where in storage would go. It's actually a catch-up function of the storage slot which you think they occupy, and you add the amount for every member you want to get back. So it's a catch-up function you need to work with, and it's not very easy. But there's also things like typed packing, which caught me out in one contract because, as you know, setting a storage slot from 0 to something else costs, I think it was 20,000 gas, and changing a storage slot which is already assigned to something else costs only 5,000 gas. So it was very confusing trying to work out, because it was squashing things like booleans and bytes and uints that are shorter than 256 into a single storage slot with some offsets. So you really need to understand how this works before you dive into that pattern. And I was talking to a trail of bits guys yesterday about the complexity that this introduces. And that it's not for everyone. It certainly has a lot of benefits, but a lot of complexity associated with it. Eternal storage is less complex, still provides a level of upgradability, but it's also valid for people who just deploy new contracts and migrate their data across. It's still okay for some people to do that. I checked this morning, the cost of writing to a storage slot is less than a cent today at current Ethereum prices. So if your migration is going to be unjustifiably expensive, then perhaps move to some of these patterns. But otherwise, it's perfectly okay to deploy a new contract and just shift all the data. It's going to cost a bit of gas, but it's simple. This is, to get here, you just need to get into Remix and make sure you understand how storage works. And then upgrades become, exponentially more kind of complex to get to. So, yeah, that's from me. I think